This question asks, in order to balance the following redox reaction in acidic solution, blank number of molecules of water must be added to the blank hand side, so left or right, of the equation. And we're given the equation. So the biggest thing here is to recognize keywords in this problem. So the keywords are acidic solution and redox reaction. And these two things are telling us to break this down into half reactions. We have an oxidation reaction happening, we have a reduction reaction. We can split this into two and make our lives a lot easier. So the first thing we can do is split into half reactions. And we can do that by assessing our oxidation numbers of each of these species and finding out which is the oxidized half reaction, which is the one being reduced. So the best thing to do that is just take each species and say, okay, well, for oxygen, I know it has a -2 oxidation number, and I have 3 of them here, so in total, it's contributing a -6 oxidation number. This is neutral, so we know that these 2 arsenics in total have to have a +6 oxidation number. So that means that each arsenic has a +3 oxidation number. And then moving on to nitrate, in a similar way, oxygen has a -2 oxidation number. We have 3 of them. And you always have to look at the charge because this has a overall -1 charge. So therefore nitrogen should have a +5 charge, or excuse me, oxidation number. And now moving on to arsenic acid, I usually just keep starting with oxygen. Again, -2. We have 4 of them to contribute a -8 oxidation number overall. We know that hydrogen has a +1 oxidation number. We have 3 of them, so that's contributing a +3 oxidation number overall. And because this is neutral arsenic, therefore, will have a +5 oxidation number. And last but not least, we are going to do the same thing here. We have a +1 from hydrogen. We have a -4 overall from our oxygens. So nitrogen now has a +3 oxidation number. So now that we did that, we can divide it into half reactions. We know that what's being oxidized, which is losing electrons, is arsenic, just based on the fact that it went from a +3 to a +5 oxidation number. And in a similar way, we know what's being reduced, which is gaining electrons, is nitrogen, which is going from a +5 to a +3 oxidation number. So I'm going to divide this page into half reactions to make things a bit more organized. So our first one is arsenic tetroxide to our arsenic acid. And I apologize for this getting really cramped. And our second one is what is being reduced. Okay, so the first thing that I like to do is balance the main elements. And this is, I call them main elements because this is pretty much everything besides oxygen and hydrogen, because those have specific rules to them that we'll deal with afterwards. So when it comes to our first equation, we're just going to add a stoichiometric coefficient of 2 to our right-hand side to balance our arsenics. And then our second equation, we are balanced. Besides oxygen and hydrogen, our nitrogens are balanced, so we don't have to worry about that. So now that we've done that, we can balance oxygen. And we can do that by adding water molecules. So we know that we have 3 oxygens on our left-hand side. We have 8 on our right-hand side. So we are going to add 5 water molecules to our left-hand side. And we can do that for our next half reaction. So we have 3 oxygens on our left, 2 on our right. So we're going to add 1 water molecule to our left-hand side. Okay, so now that we've done that, the third thing we can do is to balance hydrogen. And this comes into play based on if we're in an acidic solution or if we're in a basic solution, which is why it's so key to recognize that word in the problem statement. So because we're in an acidic solution, we're going to balance hydrogens based on hydrogen ions. So if we look at our first half reaction, we have 10 hydrogens on our left, we have 6 on our right. So what we're going to do is include another 4 hydrogen ions to our left-hand side. And similarly, for our second half reaction, we have 3 hydrogens on our right-hand side. So we're going to add 3 hydrogen ions to our left-hand side to balance this. And the last thing that we can do is to balance the charge. So we want to be dealing with neutral reactions. So for our first half reaction, we have a +4 charge on our right-hand side due to these hydrogen ions that we added. And we don't want that. We want to neutralize that side. And we're going to neutralize by adding electrons. So we're going to add 4 electrons to our right-hand side to neutralize the charge. And for our second half reaction, we're going to do the same thing. We have a +3 charge from our hydrogen ions right here. We have a -1 charge from our nitrate. So overall, we have a +2 charge. We want that neutralized. So I'm going to add 2 electrons to this side. Okay, so now we've gone about balancing our half reactions. And the very last thing that we're going to do is add our equations together in such a way that we cancel the charge. So we don't want to be dealing with these electrons that we've added. We don't want those in our final equation. So what we do is we take our equations, and I'll write them out. Okay, so here's our first equation that we came up with. And our second equation I'll write out. And we can see that we have 4 electrons on our right-hand side for our first equation. We have 2 electrons on our left-hand side for our second equation. So we're just going to multiply this entire second equation that we have by 2. And that way, these electrons will end up canceling with these electrons, and we won't have to worry about that. So when you finally add all of these, and I'll just write this on a new piece of paper so it doesn't get too cramped, you're going to get this equation. A lot of things will end up canceling out. This is an H, sorry. Okay. So you know that we have 5 water molecules on our left-hand side. We know we have 2 on our right-hand side, so you can see how those will cancel each other out, some of them. So overall, we need 3 water molecules on our left-hand side.